Have you ever looked up at the night sky, at that sprawling, endless canvas of stars and galaxies, and wondered what it all really is? We humans have been asking that question for millennia. Is it the work of a divine creator? A cosmic accident? Or could it be something else entirely, something straight out of science fiction? Imagine for a moment that everything you see, every star, every planet, your own hand in front of your face, is not fundamentally real in the way we think. Instead, imagine it's all part of an incredibly sophisticated computer simulation. This is the core of the quantum simulation hypothesis. It's the idea that our universe, with all its intricate laws and baffling mysteries, is being run on some kind of unfathomable cosmic computer. This isn't just a late-night dorm room conversation anymore. Some of our most brilliant minds in physics and philosophy are taking it seriously. The idea proposes that reality is fundamentally made of information, just like a video game is made of bits of data. The laws of physics, those elegant equations that govern everything from falling apples to exploding stars, aren't just descriptions of reality. In this view, they are the very code that programs reality into existence. Our universe operates on a set of rules, and these rules are so precise, so mathematical, they look a lot like the algorithms that run software. It's a mind-bending thought, suggesting we might be living inside a vast computational structure. So what does it mean to be a quantum simulation? This is where it gets really interesting. At the smallest scales of reality, things get weird. Particles can be in multiple places at once. They can be instantly connected across vast distances. The very act of observing them changes what they do. This strange probabilistic world is described by quantum mechanics. The theory suggests that if our universe is a simulation, it's not running on the simple on or off logic of a classical computer. It's running on a quantum computer, one that uses the bizarre rules of the quantum realm as its operating system. The universe wouldn't be rendered in simple pixels, but in fuzzy, probabilistic qubits. This concept forces us to redefine what we mean by real. If we are simulated beings in a simulated universe, does that make our lives, our thoughts, our feelings any less meaningful? Most proponents of the idea would say no. The simulation is our reality. The love you feel for your family is real. The pain of a scraped knee is real. The awe you feel gazing at the cosmos is real. It would simply mean that the ultimate substrate of our reality is not matter and energy, but information being processed according to a set of programmed rules. It reframes our place in the cosmos, not as a random fluke, but perhaps as a deliberate creation of an entirely different kind of intelligence. Think about the software on your computer. It's a set of rules, a program that tells the hardware what to do. It dictates the logic, the limitations, and the possibilities within its digital world. Now, let's look at the universe through that same lens. The laws of physics, like gravity and electromagnetism, act like the high-level programming language of our cosmos. They are consistent, predictable, and universal. But what is the underlying machine code? What is the most fundamental set of instructions? Many physicists would point to quantum mechanics. Its rules are the foundational logic that everything else is built upon, the ultimate source code that dictates how matter and energy behave at the most granular level. Consider the strange feature of quantization. In our world, things don't just come in any old amount. Energy, for instance, comes in discrete packets called quanta. You can have one packet, or two, or three, but you can't have 1.5. This is like the pixels on a screen. You can't have a pixel that's halfway between two spots. It's either here or there. This discreteness, or pixelation of reality, is a core feature of quantum mechanics. It suggests that the universe has a finite resolution, a smallest possible unit. If reality were a simulation, this is exactly what you might expect. A simulation can't have infinite detail. It has to be built from a finite number of basic components, just like a digital image is built from pixels. Then there's the observer effect, one of the most baffling aspects of quantum physics. A particle like an electron doesn't have a definite position until you measure it. Before that, it exists in a cloud of possibilities, a state called superposition. The moment you look, it snaps to a single location. This sounds suspiciously like how a video game might render its world, A game doesn't calculate the position of every leaf on every tree in the entire game world all the time. That would be a colossal waste of computing power. Instead, it only renders the details when a player looks at them. Could the universe be doing the same thing, conserving its computational resources by only defining reality when something observes it? Finally, we have quantum entanglement, what Einstein famously called spooky action at a distance. You can link two particles together in such a way that they share a single quantum state. If you measure a property of one particle, you instantly know the state of the other, no matter how far apart they are, even if they're on opposite sides of the galaxy. This seems to violate the cosmic speed limit, the speed of light. But in a simulation, this isn't so strange. The particles aren't sending a signal. They are 2 points referencing the same line of code. Changing one variable in the code could instantly update the other, because their distance in the physical world is irrelevant to their connection within the program's underlying logic. For most of human history, we thought the universe was made of stuff, tiny, indivisible atoms, or perhaps just pure energy. But a revolutionary idea has been gaining ground, championed by physicists like John Archibald Wheeler. He famously coined the phrase "it from bit," which beautifully captures the core concept, that everything we perceive as physical, the it, derives its existence from information, from bits. A bit is the most basic unit of information, a simple yes or no, a 1 or a 0. The IT from bit hypothesis suggests that at the bottom of it all, the universe isn't made of matter or energy, but of information. The physical world, in this view, is an emergent property of informational processes. This idea completely flips our traditional understanding of the cosmos on its head. It means that a particle, like an electron, is not a tiny solid ball. Instead, it's a collection of information. Its properties, its mass, its charge, its spin, are just bits of data. When particles interact, it's not two things bumping into each other. It's their underlying informational states being updated according to the rules of the program, the laws of physics. The universe then becomes a giant information processor. Every physical event, from a chemical reaction to the formation of a star, is a form of computation, a manipulation of these fundamental bits of reality. If the universe is a simulation, it's likely not a classical one built from simple bits. It has to be a quantum simulation built from qubits. A classical bit can only be a 0 or a 1. A qubit, the basic unit of quantum information, is far more powerful. Thanks to the principle of superposition, a qubit can be a 0, a 1, or both at the same time. This allows for a level of complexity and computational power that dwarfs any classical computer we can imagine. If the fabric of reality is woven from qubits, it would explain the inherent fuzziness and probabilistic nature of the quantum world. Reality isn't a fixed set of ones and zeros. It's a dynamic, shimmering superposition of infinite possibilities. This perspective, where information is king, offers elegant solutions to some of physics' biggest puzzles. The holographic principle, for instance, suggests that all the information needed to describe a volume of space can be encoded on its two-dimensional boundary. It's like a three-dimensional hologram projected from a two-dimensional surface. This is a profound statement about the nature of information and space. It implies that information, not space or volume, is the more fundamental quantity. If reality is a simulation, the holographic principle might be a clue about how its data is stored and managed, a cosmic compression algorithm to make the simulation run efficiently. The reason we even entertain such a radical idea is that the universe keeps showing us features that look suspiciously like they belong in a computer program. We've already touched on a few, but they bear repeating because they are so central to the argument. The universe seems to have a maximum speed limit, the speed of light. Nothing with mass can reach it, and information cannot travel faster. In a simulation, a processing speed limit makes perfect sense. No computer is infinitely fast. There has to be a maximum rate at which the simulation can update its state from one moment to the next. The speed of light might just be the clock speed of our cosmic processor. Then there is the pixelation of reality itself. The Planck length, about 1.6 times 10 to the minus 35th meters, is the smallest possible distance that has any physical meaning according to our current theories. Below that scale, our concepts of space and length break down. Similarly, the Planck time is the smallest unit of time. It's as if the cosmic simulation is running on a grid, and the Planck scale represents the size of the individual pixels of space-time. You can't have a location between pixels or a moment between frames. This inherent discreteness, this finite resolution of the universe, is a powerful hint that reality might be computationally generated rather than being infinitely smooth and continuous. The fine-tuning of the universe is another major piece of the puzzle. The fundamental constants of physics, the strength of gravity, the mass of the electron, the cosmological constant, are all exquisitely balanced. If you were to change any of them by even a tiny fraction, the universe as we know it could not exist. Stars wouldn't form, atoms would fly apart, and life would be impossible. This incredible precision looks less like a random cosmic accident and more like someone deliberately set the parameters. In a simulation, these constants would be the initial values plugged into the program. Their fine-tuning might be evidence that they were chosen specifically to create a universe that is complex and interesting. Finally, the very language of the universe seems to be mathematics. As physicists have dug deeper into the nature of reality, they haven't found gears and levers, they've found equations. The behavior of everything from subatomic particles to galactic clusters can be described with stunning accuracy by abstract mathematical structures. Why should this be? Why is the universe so comprehensible in the language of math? If the universe is a product of computation, then its foundation would naturally be mathematical. The underlying code is math. In this light, the unreasonable effectiveness of mathematics in the natural sciences is not a mystery at all. It's exactly what we should expect to find. While we don't have a smoking gun, there are several compelling lines of argument that lead serious thinkers to consider the simulation hypothesis. Perhaps the most famous is the philosophical argument from Nick Bostrom, a professor at Oxford University. His simulation argument doesn't claim we are in a simulation, but rather that one of three possibilities is almost certainly true. First, civilizations like ours almost always go extinct before developing the technology to create realistic simulations. Second, advanced civilizations lose interest in running such simulations. Or third, we are almost certainly living in a computer simulation. Bostrom's logic is powerful. If a civilization can survive long enough to develop this godlike computing power, they would likely run countless simulations of their ancestors or of other possible universes. Just think about how many video games and simulations we run with our primitive technology. An advanced civilization could run billions or trillions of them. If that's the case, the number of simulated realities would vastly outnumber the one base reality. Therefore, based on simple probability, it's far more likely that we are in one of the many simulations than in the single, original universe. It's a statistical argument that is hard to ignore. As we discussed, the holographic principle provides a more physics-based line of reasoning. Stemming from the study of black holes, it suggests that our three-dimensional reality might be a projection of information stored on a distant, two-dimensional surface. Imagine a hologram. The three-dimensional image it creates is entirely encoded on a two-dimensional film. The universe could be a grand-scale version of this. Our perception of depth and three-dimensional space might be an illusion, a clever rendering trick of the cosmic program. This idea, which is a serious contender in theoretical physics, aligns perfectly with the notion of a universe whose fundamental reality is informational and computational. The parallels with our own technological progress also provide food for thought. We are already building quantum computers. These machines, while still in their infancy, operate on the same principles of superposition and entanglement that govern the universe at its most fundamental level. We are learning to program reality on a small scale. As our quantum computers become more powerful, we might one day be able to simulate a small, simple universe of our own. If we are on the verge of becoming creators of simulated worlds, it stands to reason that another, more advanced civilization may have already done the same, and that we are one of their creations. Our own technological trajectory makes the simulation hypothesis seem less like fantasy and more like an extrapolation of our own future. For all its intriguing possibilities, the simulation hypothesis faces a mountain of skepticism, and for good reason. The most significant challenge is that the theory may be fundamentally unfalsifiable. A core principle of the scientific method is that a hypothesis must be testable. It must make predictions that can be proven wrong. But how could we ever definitively prove we are not in a simulation? Any evidence we find, any experiment we conduct, could simply be part of the simulation's code. If we discover the pixels of space-time, a skeptic could argue that's just how the base reality works. The creators of the simulation could even alter the program to hide the evidence as we search for it. A theory that can explain everything explains nothing. Another major objection is the sheer scale of the computational resources required. To simulate a universe as vast and complex as ours down to the quantum level would require a computer of unimaginable power. Simulating the quantum state of just a few hundred particles is already beyond the capacity of the most powerful supercomputers on Earth. To simulate the trillions upon trillions of particles in our observable universe, interacting in real time for 13.8 billion years, seems computationally impossible. Even if our simulators exist in a universe with different laws of physics, the scale of the task is so staggering that it pushes the boundaries of credibility for many scientists. The principle of Occam's razor also presents a problem. This philosophical rule suggests that when faced with competing explanations, the simplest one is usually the right one. The idea that there is a base reality with a super-advanced civilization running a universe-sized computer on which our reality is a program is an extraordinarily complex explanation. It adds layers upon layers of new, unproven entities. Isn't it simpler to assume that this universe, the one we observe, is the one and only base reality? Proposing an entire unseen level of existence to explain our own may be an unnecessary complication, a solution in search of a problem. Finally, there is the profound mystery of consciousness. What is it? Where does it come from? If we are simulated beings, is our consciousness real, or is it just a clever illusion programmed into our code? Can a simulation truly replicate subjective experience, the feeling of being me? This is the hard problem of consciousness, and it becomes even harder in a simulated reality. Are we just sophisticated chatbots acting out a script without any genuine inner life? Or would our simulators have to solve the riddle of consciousness to create us? The hypothesis raises more questions about our own nature than it answers, pushing this deeply personal mystery into an even more abstract realm. So, where does this leave us? Are we living in a cosmic computer program, or are we the product of natural, unguided physical laws in a base reality? The honest answer is, we don't know. And that's okay. In fact, that's the whole point of science. The quest for knowledge is not about having all the answers, it's about asking the best questions. The simulation hypothesis is one of the grandest questions we can ask, forcing us to confront the very nature of existence. It pushes the boundaries of physics, computer science, and philosophy, creating a fertile ground where these disciplines can meet and challenge one another. This is not the first time humanity has had its worldview turned upside down. We once believed the Earth was the center of the universe, until Copernicus and Galileo showed us we were on a small planet, orbiting an ordinary star. We once thought space and time were absolute, until Einstein revealed they were relative. Each of these shifts was met with resistance because they demoted our special place in the cosmos. The simulation hypothesis is perhaps the ultimate demotion, from the center of the universe to a random planet, to a potential character in someone else's computer game. But each demotion has also brought a deeper, more profound understanding of the universe. Whether the hypothesis is ultimately proven, disproven, or remains a tantalizing mystery, its value is undeniable. It encourages us to think critically about the world we take for granted. It inspires us to look for the seams in the fabric of reality, to search for the telltale signs of a constructed world, like glitches in the matrix or the fundamental pixelation of space-time. This kind of curiosity is the engine of scientific progress. It's what drives us to build better particle accelerators, more powerful telescopes, and smarter quantum computers. The tools we build to test this wild idea might lead us to discover something else entirely, something even more wonderful and unexpected. In the end, the journey is just as important as the destination. To contemplate the simulation hypothesis is to participate in one of the oldest and most noble human traditions. To look up at the heavens and ask, "What is all this?" It connects us to the ancient philosophers who wondered if the world was just shadows on a cave wall, and it propels us toward a future where we might one day create universes of our own. So keep looking up, keep asking questions. The cosmos is full of mysteries, and the greatest adventure is not just discovering the answers, but having the courage to imagine the possibilities. The universe is the ultimate puzzle, and we, perhaps, are the universe's way of trying to solve itself.